Welcome to G Fun Facts Online, your go-to source for mind-bending science and incredible tech. Today, we're diving deep into the world of the super tiny, exploring materials that could revolutionize how we power our planet. We're talking about carbon nanotubes, or CNTs, and a truly fascinating trick they can perform with light. Imagine taking low-energy light, the kind that solar cells usually struggle with, and upgrading it into more powerful, useful light. Sounds like science fiction, right? Well, it's called Upconverted Photoluminescence, or UCPL, and it's very real. So let's start with the basics. You've probably heard of photoluminescence. Think of fluorescent paints. They absorb high-energy light, like UV light from a black light, get all excited, and then release that energy as visible light, which is lower in energy. Inside these materials, the absorbed light excites electrons, creating these little energy packets called excitons. When these excitons relax, they emit light. Standard stuff. High energy in, lower energy out. But upconversion photoluminescence, UCPL, flips this on its head. It's a much rarer and, frankly, cooler process where materials absorb low-energy light and then emit higher-energy light. For solar energy, this is a game changer. A huge chunk of sunlight is low-energy infrared light, which typical solar cells just can't use effectively. UCPL means we could potentially capture this wasted energy, convert it into a more usable form, and give solar panel efficiency a serious boost. And this is where our tiny heroes, single-walled carbon nanotubes, SWCNTs, come into play. Scientists, like those at the Riken Center for Advanced Photonics, have been digging into how these nanotubes pull off this upconversion feat. It turns out, the secret lies in a beautiful dance between light particles, or photons, and vibrations within the nanotube structure, called phonons. Here's how it works, according to the latest understanding. First, a low-energy photon, say from infrared light, hits the carbon nanotube and excites an electron. But here's the clever bit. At the same time, this electron gets an extra energy kick from a phonon, one of those lattice vibrations. This combined energy boost pushes the electron into what's called a dark exciton state. Now, dark here means it doesn't like to emit light directly. After a tiny bit of energy adjustment, this exciton then transitions to a different state from which it can efficiently emit light. And crucially, this emitted light has more energy than the light that was initially absorbed. This whole process is intrinsic to the nanotubes themselves. They don't even need defects, which was a previous theory. It seems specific vibrations, known as K-momentum phonon modes, are central to making this magic happen. What's also interesting is the role of temperature. Researchers found that if you heat up the carbon nanotubes, the UCPL effect gets stronger. This makes perfect sense with the phonon-assisted model. Higher temperatures mean more lattice vibrations, so more phonons are available to give that necessary energy boost to the electrons. It's like having more tiny springboards ready to launch the electrons to higher energy states. So why is this such a big deal for solar energy? Well, as we've touched on, imagine solar cells that can now use all that abundant infrared light that's currently going to waste. This could mean a significant jump in how much electricity we can get from the sun. Plus, by utilizing a broader spectrum of sunlight, solar cells could perform much better in various light conditions, not just under perfect, direct sunshine. But the potential of UCPL in carbon nanotubes doesn't stop at solar panels. Think about biological imaging. Near-infrared light can penetrate much deeper into biological tissues than visible or UV light, and it causes less background noise or autofluorescence. If you have nanoparticles that can absorb this deep penetrating near-infrared light and upconvert it to visible light, you've got a powerful tool for looking inside living organisms. Beyond that, this ability to manipulate light energy could lead to entirely new types of photonic devices. There's even research into using laser illumination to pull thermal energy out of nanotubes via UCPL, a concept known as laser cooling. Imagine cooling down electronics with light. The study of how light interacts with carbon nanotubes, especially this upconversion phenomenon, is a super active area of research. Scientists are now focusing on making the upconversion process even more efficient, figuring out the best ways to build these nanotubes into actual solar cells and other devices, and even trying to engineer the interactions between light, excitons, and phonons to control the upconversion for specific needs. And it's not just carbon nanotubes. Researchers are also looking into other nanomaterials, like carbon quantum dots and rare earth-doped nanoparticles, each with their own unique ways of upconverting light. The journey to understanding and harnessing upconverted photoluminescence in carbon nanotubes is paving the way for a future with more efficient solar energy and a host of next-generation photonic technologies. This new, clearer picture of how phonons and dark excitons work together is a massive step forward. That's all the time we have for today on Fun Facts Online. We hope you're as excited about the potential of these tiny tubes as we are. Join us next time for more amazing science stories. Thanks for listening.